Log on, tune in, find out. Another good idea from Cambridge.
From UC Riverside, she will speak on Yangians and Dorey.
So, it's very nice to be here, and I'm very glad the organizers gave me a chance to visit Cambridge and give a talk at this meeting. So, for the most part, I'm going to be talking about fairly old work and an old conjecture. Part of the reason is it's particularly, I think, suited to this conference, which is in physics and Lie theory. And it's a nice conjecture and representation theory, which was made by the British mathematical physicists, Braden, Dorey, and Mackay. So it's so they made the conjecture for Yangians, and so that's why my title said Yangians, but I'm going to actually talk about it for quantum affine algebras. And the reason for that is because the later literature is all for quantum affine algebras and not for Yangians. Okay, so another reason for talking about this old work is that that conjecture was quite general. And so Presley and me, I guess in 96, we proved special cases of this conjecture. But the other cases are still unknown. And so, but it's not established in other situations. And in recent years, there's been so much literature on representations of quantum affine algebras that perhaps it's reasonable to expect that one can solve this conjecture more fully. So this is one reason, this is the real reason that I went back to talking about this old work. So to set this all up, I of course need endless notation. So we'll have G will be a simple Lie algebra, and H a Cartan subalgebra. And we'll fix a set of simple, so I will denote a set of index set for simple roots. And alpha I will be the simple roots, and alpha I check the co-roots. And we'll need the dominant integral weights. So, yep, and then there's P plus the weight lattice and Q plus the root lattice. So this is the weight lattice and the root lattice. LG is the loop algebra. So this is a loop algebra, G tends to C to T inverse. Okay. So I'm going to be interested in the quantum versions. Oh, good, this is made for short people. Okay, so I'm going to be interested in the quantum versions of this. So UQG will be the quantized enveloping algebra of G, and UQ of LG, the quantized enveloping loop algebra. And we'll have inclusions over that. So this is given by some fairly horrible generators and relations, which I don't intend to write down, but I will write down the generators. So we have generators xir plus or minus, and you have one of these for each I in I and r in the integers. We have ki plus or minus 1. So far, these look like the Drinfeld generators, but then we have one which is not, which I'm going to call PIR. So this is for I in I and R in Z. And PI0 is always assumed to be 1. Okay. So these things generate the quantum loop algebra. These are what are called the integral imaginary root vectors. And for my purposes, it's more convenient to work with these generators. Okay. So let's see. So for every lambda in P plus, we have an irreducible representation, V lambda. So it's an irreducible finite dimensional representation of UQG. And the other fact that we need to know is that about representations of UQG is that any representation, finite dimensional representation of UQG is semi-simple. Okay. So, well, okay. So the category that I'm going to be interested in is, so it's going to be F. It's a category of finite dimensional modules for UQ of LG. And so this is an abelian tensor category. So this is abelian tensor, and it has duals. This is because UQ of LG is a Hopf algebra. So the basic problem can be formulated as follows. It's sort of very standard and natural. So the basic problem we're trying to understand is, supposing I take three simple objects in F, which are simple. When do I have the trivial module sitting inside it? So when is? And when it is non-zero, you'd also like to know what the dimension of the space of invariance is. Okay, so what Dorey's rule, so the work of these people, their conjecture was to give a necessary and sufficient condition. So for this, but under certain restrictions. So for this, for certain kinds of U, V, and W. So I will tell you exactly what kind it is in a minute, but one can actually do a bit better. So that would be the next part of the talk. The next part of this program that I want to talk about, which is one can also give conditions on U and V, so that the only time this holds, so that Hom U Q L G, C U tensor V tensor W is non-zero, is when W is what you expect it to be, the dual of U tensor V star. So you always have to be careful about left and right duals because our algebras are not co-commutative. But this was the, so this is the other thing. So, what this tells you actually is that U tensor V must actually be irreducible, because my problem is when U, V, and W are all simple. Okay? So it's a question, so you can think of this as a condition for this tensor product to be irreducible. So, no, that's no good. Okay. I suppose my students are having a good laugh at that. Thank you. Yeah, I'll be able to put that down. Okay. Okay, so to be able to formulate all these conjectures, I need to know what the simple objects in F are. So that's so the simple objects So to describe them, it's convenient to introduce what the analog of the weight lattice for quantum groups. So P, so the correct analog is the following. So we let P be the free abelian group. So generated by some elements which we call pi IA, and you take one for each element of I and one for every non-zero complex number. Okay. And P plus will be the will be the monoid generated by these things. Okay. So for every element of P plus, then we're going to associate. So given a pi in P plus, we're going to associate to it two modules. One which we'll call W pi, which is the while module. And then the other one, which we call V pi, and that's the irreducible module. So the definition of W pi is quite simple. So W pi is given by generators in relations. So it's generated by an element, let's call it W pi. And it has relations. So you demand that the XIR pluses kill it. You put in a certain condition, and I've forgotten to define something, so I'll define that in a minute. So this is weight pi plus 1, W pi equal to 0. And these elements, PIR, the integral imaginary root vectors, act as some scalars on it. So what is weight pi? So weight is going to be a homomorphism, which will go from my lattice, which I associate to this category F, to P, and it will just be defined by weight of pi IA will be omega I. So it's like the, so this is sort of the fundamental weight with that parameter. Okay, so weight pi, so this doesn't make sense either. So this is weight pi. You evaluate it at the co-root alpha I check, which you can do because this is an element of P plus, and then you add 1. So the only missing information here is I haven't told you what the relation between PIRs and pi is. So the PIRs, so the AIR, are given as follows. So you form the power series, r greater than or equal to 1, AIR u to the r. And this has got to be equal to, so this has got to be equal to product over r greater than or equal to 1, 1 minus, so dir u. Okay, and what is this dir? So remember, if I have pi, it's an element of P plus. So that means I can write it as a product of the generators. So this is pi I dir. Okay, so I product over dir. So I have an element of my lattice. I write it out as a product of generators, and then I concoct a polynomial out of that. And I want these two to be equal. So that's W pi. So then the theorem, which was proved at various times with Presley between, 90 and 2000, was that, so if you take pi in P plus, then W pi is finite dimensional, so it's an object of F. It has W pi has a unique irreducible quotient. which we call V pi. And these V pi's, any simple object in V is isomorphic to V pi in F is V pi for some pi. Okay. So now the Weil modules, so as I said, so the Weil modules were only defined sometime around 2000, and they're well understood by now. So the modules W pi are well understood. So let me tell you what we need to know about these modules for the moment. So supposing we take one of our generators and ask ourselves what the Weil module here is, W pi IA, then one actually knows that it's irreducible, and this is isomorphic to V pi IA. And the other part that one knows is, if you take an arbitrary pi, then you know that W pi is just isomorphic to a tensor product of the fundament of these kinds of Weil modules. So it's isomorphic to a tensor product of W pi IAs. So I in I, A in C star. So I'm being quite careless over here. What I really mean is we have to write pi as this product, pi IA, and then we have to take this tensor product in a particular order. So it won't be true for all orders that this tensor product is isomorphic to W pi, but if you choose your orders correctly, it's true. And then it's also isomorphic to V pi IA by part 1. Okay. So this was proved by Presley and myself, and then later by me. Or anyway, it was proved for classical types. Okay. And this was conjectured and proved for SL2 by us. So conjectured and proved for SL2. So it was conjectured for all G and proved for SL2. Okay, and this actually appeared in the, I guess, in the Durham proceedings in '99. But now this is, in a complete generality, this is deduced from the work of Beck and Nakajima. So this was in 2005 or 4. I think Kashiwara needs to be there somewhere as well. But, all right, so Dorey's rule then can be interpreted as follows. So Dorey's rule, in some sense, can then be interpreted as the question, when is Hom CW pi not equal to 0? So I should say that W pi is generically irreducible, but not always. So W pi is not necessarily isomorphic to V pi. So this question is quite sensible. Okay. So let's see. So when does this question first begin to make sense? Well, if you take pi to just be pi IA, then what this tells us is that the Weil module is irreducible, and so you're obviously not going to have the trivial module sit inside it. Okay? So then the answer is never. If you take pi to be a product of two things, so let's say pi IA and pi JB, then what is the question? The question is, when is Hom sitting in, when is the trivial module sitting inside V pi A tensor V pi JB. But this is again easy to answer. This is exactly when the two modules are dual. So this is if and only if V pi A is isomorphic. So again, one has to be careful. Let's assume everything is correct. So it's isomorphic to V pi JB dual. Okay. That's the only thing that you're going to get out of that. So the first interesting case then of this problem. Okay. Yeah. So the first interesting case of this problem is when you have three things. So supposing we're doing pi equal to pi IA, pi JB, and pi KC. Okay. So then so here's the conjecture that they made. So hom U Q L G of C V pi IA tensor V pi JB is non-zero if for some choice of A, B, and C, if and only if the following holds. We have 0 belongs to gamma omega I plus gamma omega j plus gamma omega k, where so gamma is a subgroup of the Weil group of G. Okay. Generated by a Coxeter element. So this is really quite a remarkable conjecture. I mean, well, I still don't know why it's the Coxeter element that plays a role, but it does. And this condition, of course, appears to depend on the choice. There are many Coxeter elements in your Weil group, and so this condition would appear to depend on the choice of Coxeter elements, but in fact it doesn't. It's all completely independent of the choices that you make, and so this is the so this was their conjecture. And so if you look at it for a moment, it looks a lot like the PRV conjecture. So what does the PRV conjecture say? So PRV. So the PRV conjecture is, of course, a theorem now due to Kumar and so let's Matthew. So the PRV theorem says the following. Suppose if you want to know when you have C sitting inside V lambda tensor V mu tensor V nu, then this happens is non-zero if 0 belongs to W lambda plus W mu plus W nu. Okay. But this is actually much weaker than this condition. So they're not equivalent even when you restrict yourself to fundamental weights. So PRV is weaker than Dorey. Using the Coxeter element. So the first time I think you see this is if you look at D5.
When you say Coxeter element,
yeah,
Coxeter element
product of simple
roots or conjugate?
Product of simple reflections. One.
Normally a Coxeter element could be a product of conjugates of simple roots.
No.
And presumably here you want
simple. Well, if you take conjugates, then you just go to a different root system. I mean,
yeah, but then you have fundamental weights here, so that would
not work. No, well, it's supposed to. I think there's a result in our paper which says it's independent of all choices. But I don't, yeah. But anyway, certainly here I mean product of simple reflections, distinct simple reflections. Okay, so the first time you see that this condition is weaker than Dorey's condition is in D5. So the Dinkin diagram of D5 is the following. This is the adjoint representation. So omega 2 is the adjoint representation. Okay. And we certainly have 0 belonging to W omega 2 plus W omega 2 plus W omega 2. But it doesn't belong to gamma omega 2 plus omega. So in particular, so it's really telling you that there are fewer things appearing in the tensor product than in the classical case. Oh. Okay. Okay, so the most general form of, so you can imagine now what the most general form of that conjecture is. You just take arbitrary things and arbitrary numbers. And I should say that all my comments are correct for simply laced algebras. For non-simply laced algebras, one has to introduce a twisted condition, which I don't want to go into. So let's just assume for convenience that G is simply laced. The non-simply laced cases have their own conditions. Okay, so the most general forms as that Hom UQLG of C V pi I1 A1 tensor, etc. is not equal to 0 for some choice of A1 up to AK. If and only if 0 belongs to the sum of these.
But the PRV is not if and only.
No, it's not if and only if. If, I only said if.
I hear you're saying if.
Yeah, for Dorey it's if and only if. Yeah. So this is the most general form of their conjecture. Okay. Okay. So I want to keep this conjecture up. So Presley and I proved this. So for k equal to 3, and for G of classical type, this is a theorem. But we couldn't do very much for the exceptional algebras, and I want to explain why. And we certainly couldn't do anything in the general case of K. Okay. So one of the reasons we couldn't do anything, one of the many reasons we couldn't do anything is there weren't enough tools, really. So how would one try to, so let's just look at, so how would one try to prove that this tensor product contains V omega I pi? Okay. So one way to try and do that, well, so if this is non-zero, then what is sort of clear is that this implies that, let's say that this tensor product is not irreducible. So if you knew it was irreducible, if you knew it was reducible and where it was reducible, for what values of A and B, then you could try and perhaps look for that particular representation to appear. Okay. So this was our approach. And we could answer this question. So this question could be answered for classical types, because one really knew what these modules look like, because the structure of V pi I A was known, as well as points of reducibility.
Is it obvious that if you just kill A, B, and C and reduce to U of Q of G, that the condition of non-vanishing on, say, this board is equivalent, is forces a condition of non-vanishing on the other? In other words, if I forgot about A, B, and C,
Yeah.
and I replace L of G by G, then the non-vanishing here would be necessary to have non-vanishing.
That's right. Yep. Okay, so in the exceptional case, so this was done in 96, as I said, and the exceptional, at that point, nothing was known about the exceptional cases. But absolutely not understood. There was not even a conjecture on what these modules look like. That conjecture came in 99 from the work of Ocado and company. Okay, so there's another thing that's sort of slightly wrong with Dorey's conjecture, or the conjecture of Brady, Mackay, and Dorey, and that is really this non-vanishing of this tensor product of this Hom should be a condition on IA, JB, and KC, rather than just on I, J, and K, right? Because it's a tensor, because that representation depends on all those parameters. So it only says that it's non-zero for some choice if and only if this happens. A better statement would be it's non-zero, which included the condition on parameters, right? So that was the other thing that's not very satisfactory about that. So what I want to now do is try to persuade you that all these problems have now gone away, and that one should really be able to answer more general versions of the more general conjecture. Okay. Not that I can answer it, but in preparing this talk, I realized that perhaps one didn't have all the ingredients necessary to answer it. Okay, so let's go back to my basic problem, which was to understand. So basic problem number 2. So what this board is supposed to have convinced you about is that it's very important to understand when the tensor product of two finite dimensional modules is reducible. So the basic problem now to give a sufficient condition which you can actually compute for the tensor product of for V pi tensor V pi prime to be irreducible. Okay, so the first thing that's sort of clear is that if you look at V pi tensor V pi prime, you can always identify a particular, it's not clear, but you can prove that you can always identify a particular irreducible constituent, and that's V pi pi prime. So we write our P plus and P multiplicatively, and so if you have two elements of it, you can multiply them, so you have another irreducible representation, and you can prove that this tensor product is, that this multiplicity is 1. So to understand when this is irreducible is equivalent, so V pi tensor V pi prime yeah. So I don't want to say that, so let me correct myself. What I do want to say is, so to answer the question when V pi tensor V pi prime is irreducible, that means when it's isomorphic, is actually equivalent to answering a slightly weaker question, so equivalent to asking not just when this multiplicity is 1, but when this is actually a quotient of this. Asking when is v pi pi prime a quotient of v pi tensor v pi prime. Okay. So in the SL2 case, this was answered a long time ago, again in 90, in the same paper with Presley. So SL2, the answer is no. It's a very simple, very elementary, concrete condition. So it's a very concrete condition which describes the points of reducibility. So I'm not going to describe this condition. I'm just going to assume that we know it. It's just not, it's quite enough as it is.
So why is this equivalent question?
Well, because, maybe, okay, so you look at the module. So I might be lying a bit. You look at the module through the tensor product of the highest weight vectors, correct? So then that will give you, that will have as quotient this module.
So that's why I didn't understand. I thought the second was always true.
No.
No?
This one? No. That's not always true. You see, if you take v pi tensor v pi prime, and you take the highest weight vectors in each place, right? And you look at this, this can be a proper submodule. It can be a strict proper submodule.
I see.
So that's why it's not true. Even for SL2, you can see that. If you take the,
Yeah.
But isn't pi prime is a universal object or something?
no, that was W.
Oh, sorry, it's not.
W. And then again you run into trouble because then you don't know that this tensor product is universal. So you have to prove all these results separately. Yeah.
So, but if it is a quotient, then it is actually isomorphic.
If it has to be a quotient of this and the other way around. So it must be a quotient of this and of v pi prime tensor v pi. Then it's isomorphic. Right.
Or it is the same time as submodule in the quotient.
I'm sorry?
You were saying first.
No, there will be duals that will come in, but it'll be the same. But the conditions will all be equivalent. Probably. Yeah. Okay. Yeah. So as I was saying, so for SL2, one has very concrete answers, and so we'll just assume that we know the answer for SL2, and I want to describe how to generalize that for G. So we'll assume this and give a sufficient condition for G.
Is it related to the question when the R matrix is regular?
Yeah. That'll when it has singular. So it's related to finding out when the R matrix has singularities.
Is it the same question or not quite?
Not quite, probably. I mean, probably it's the same question, but if it's a theorem, I don't think it's a theorem. Okay. It's certainly what one would believe. Yeah. Okay, so let me formulate this condition for that. I need to introduce, so let's see, so the while group has already appeared in this context, but the while group acts on, so W acts on P plus. Okay. So the question is, do we have a nice action? Well, this is wrong. So it acts on P, on the weight lattice. And I've introduced the analog of the weight lattice, which is suitable for my purposes. And so it's reasonable to ask if we have some analog of the Weil group action on this weight lattice. So do I have a map like this, where B is a braid group of G? So in the quantum case, it's okay to replace the Weil group by the braid group. And the answer is yes. So the braid group of G acts on my lattice P as follows. So if I take, no, this is not a reflection. If I take a generator Ti's for the braid group, how does it act on, so it's going to just act as an automorphism. So how does it act on a generator pi j a? Well, it just fixes it if j is not equal to I. And if j is equal to I, then it does something interesting. So I'll write the answer and then explain it. And then this is a product, not a pi, over all j such that aij equal to -1. Remember, I'm doing this only in the simply less case for convenience. It's pi j aq. And what this is supposed to remind you of is Si of omega I equals to omega I minus alpha I. Okay? So that's why you get an inverse over here, and these things add up. So we're rewriting things in terms of the weight lattice. So, okay. So these formulas define an action of the braid group. So this was done, I guess, this and all subsequent results in this direction were done by me in 2002. And so now one can reformulate Dorey's rule. You just, so you just replace the Weil group by the braid group. So if and only if the element 1, remember that we are in a multiplicative group, so this is 1, belongs to, so I have to, let me call this bold gamma, pi ia, pi jb, and pi kc. Where this gamma is the subgroup of B generated by, of the braid group, generated by powers of T gamma. So gamma is a Coxeter element. Well, I can't say that I've actually checked that the two are equivalent, but I have checked it enough to make me fairly confident that this is probably true. And the point about reformulating this now is I don't have to say anything about A, B, and C, because the braid group allows for the condition that 1 is involved in this. So if you notice, the braid group action changes all these scalars, right? So it sees the scalars in some way. So this condition also sees the scalars, and I'm pretty sure that this is the correct reformulation of Dorey's rule, and it's a more satisfactory reformulation, I think. Okay. So the other problem that I mentioned was that one didn't know when tensor products were reducible, and all we knew was when a pair of fundamental representations, the tensor product was reducible. And here, to do Dorey's thing in general, you need to know when an arbitrary tensor product is reducible. Okay? So to do that, I'm going to use the braid group to give you a nice sufficient condition for tensor products to be reducible. This braid group action. Okay. Right. Okay, so let's see, so I'll take W0. This is going to be my the longest element of W. And I'll fix a reduced expression. So it's SI1 up to SIN equal to W0. And then I'll take the corresponding, do that. Okay. So I have my lattice P, and inside that I'm going to define a subgroup Pi for each I and I. Okay. So this is going to be, so Pi is just going to be the subgroup generated by the elements pi I A. So we fix an I and we just vary A over all elements of C star. Okay. So now if you take an element pi in P, right, and you operate on it by a braid group element, so TW pi. So let's take pi in P plus, and you operate on it by a braid group element. This in general is not, of course, going to be in P. It's P plus. It's going to be only in P. Okay. But the following does hold. What one can prove is that, however, so one can prove the following proposition, which says, supposing I look at, so let me say this in the first case. So supposing I look at TIN of pi. Okay, I fix my reduced expression up there. Supposing I look at TIN of pi. Okay. And then, so this, and then in this, I look at only those things which involve IN minus 1. Right, so I take this element, I write it out as a product of my generators, and then I identify the things which only involve this particular root. Okay? So maybe I should just do a small calculation. So, but if I do that, then this I can prove is in pi n minus 1, IN minus plus. So there are no divisors which occur over that. So it's perhaps worth doing an example. Supposing we look at SL3, right? Then so what is this braid group act? So then W0 is S1, S2, S1. Okay. And let's look at pi 1a. Okay. So then what does the braid group action do? Well, T1 of pi 1a by my formulas is pi 1 AQ squared inverse pi 2 of AQ. Okay. And what I'm saying over here is you take T1 pi 1a and you look at the part which only involves the pi 2's, and it's a polynomial. It doesn't have any inverses in it. Okay, it's in the monomial. Okay, so this fact, and then more generally, so of course, and then this is more general, you'll have that Tij plus 1 Tin pi, and now I look at the ijth coefficient of it, and that's going to be in Pij plus. So what is the virtue of this? The virtue of this is that it gets us into an SL2 situation. Okay? So what we're looking at, in some sense, are the extremal vectors, and we're asking what the extremal vectors look like, their eigenvalues of the PIR sum. Okay. So this is quite classical idea to look at the extremal vectors. And so now the result, so that in the theorem is the following. That says that V pi tensor V pi prime maps onto V pi pi prime if the following conditions hold. So I have my data, I have a fixed reduced expression. So the following conditions hold. So I need, if the following hold for for UQ of LSL2. So I look at V pi n. So I'm going to write SL2 over here to make sure that tensor V pi VSL2 pi I n prime maps onto it okay, so I don't know a better way to say this, etc. So and then more generally, if you take SL2 pi ti, I'm running out of patience, tin pi, when you look at the ij minus 1th component, then you have a surjective map. Now I have to be careful over here. I don't need it to be symmetric. I only need pi prime of ij minus 1. So I only need to play this braid group game on one side. I don't need to play it on the other. Surjective. Okay. So, and then this is v pi tij tin pi times pi prime. Okay. All right. So this condition, of course, looks, and we know when these happen because I know the result for SL2. Okay. So this gives you a sufficient condition for what I wanted when the tensor product, when this occurs as a quotient. And the question is, can one actually work with this? Can one actually compute with this condition? And the answer is yes. Not for general pi and pi prime, but for most of the kinds we're interested in. So this condition is made completely explicit. So it's surprisingly easy to work with this condition. And so, there should be a third part, there should be another part of the theorem. So this is part A, and part B, which I need to convince you that we can do Dorey's rule now in general, is that supposing I take k of these things, okay, and I want to know when this maps onto this, okay, then I only need to be able to do it pairwise. Okay, so it's surjective if for each pair I have a surjective map. I less than j. I have this is very bad notation, so let's call this P and R. I have this. Okay. So that means that, so not only can I analyze these pairwise, I can also analyze any number of them and tell you what the points of reducibility are. Okay. So this condition, okay, so the condition is explicit. And it is written in my paper for all forms, whenever pi is of the form, when all these pi's are of the form pi I a's, and also for what I call the Kirillov-Reshetikhin modules. Okay. So in some sense, they're appropriate. So the Kirillov-Reshetikhin modules are not quite taking pi I a to the power n in the lattice, but some shifted version of them. So we won't worry about it, but it can be written. So there's some concrete finite set of points at which this tensor product could be reducible. Yeah.
But the question about this result B.
Yeah.
Does it mean that then the tensor product is reducible if any two?
Yeah.
Right, and this is true for any pi's.
With these restrictions 1 and 2.
With this restriction.
Yeah.
So if this is true, then so you check this condition for this pi's, and then this.
Yeah. So if pi and pi prime satisfy these two conditions, then the tensor product is irreducible in all. Yeah. Okay, and so this is also true for Kirillov-Reshetikhin modules. And so in fact now it seems reasonable again that Dorey's rule will predict the answer for Hom UQLG C sitting inside V pi IAN tensor V pi IJBN. So I'll still say it only for 3 things because I'm out of steam. Okay. But we do need, maybe I should have R. I do need the same R's over here, I think. If one is in my braid group orbit. So if and only if one belongs to this braid group orbit.
So again, the theorem relates to if, probably.
I'm sorry?
Theorem is sufficient.
Yeah, the theorem is sufficient, and I think for fundamental modules, it's probably necessary. Yeah, for fundamental modules, it's probably necessary. For the classical cases, this is correct. I don't know, exceptional cases, I don't know. But yeah, but in general, I certainly don't know. Okay, and so this is a possible generalization of Dorey's rule, and I'm done. Thank you.
I guess one would like to do this with crystals, especially since the last lecture. The Littleman path model gives a very good way of getting the Kumar result.
Mm-hmm. Yeah.
Is there any relation between these conditions 1, 2 and our matrices? Because basically our matrices provide similar results, but if you can compute them.
Yeah, I don't know how you compute our matrices in this kind of generality for arbitrary pi.
But this is SL2 only, and
yeah, but yeah, it's an SL. Yeah, so I don't know what the R matrix. I mean, how you would do this in the R matrix language. But yeah, it is only an SL2. It's an extremal weight thing. So, but I don't know how you do it.
Could you say what is known for the non-simply laced case?
So Dorey's rule for k equal to 3 is known for the non-simply laced case. So for B and C, you have to have the condition is not enough. You have to have a twisted condition as well. So that you.
So have you been able to reformulate it?
Oh no, I've been thinking of this only now. So no, I haven't. But I suspect. I mean, that condition I think just goes to the dual while group, and it involves picking correct things. So I suspect it'd be the same kind of thing, but I don't know.
So is there any kind of, is it possible to have any kind of theory which would tell you not only, well, this theory tells you when an irreducible module occurs in the socle of the tensor product. We might ask when an irreducible module occurs in, you take the socle filtration, and when it occurs in the, say, kth term of the filtration. So we have some kind of polynomial that would tell you that. So do you think that such a theory which would extend this is possible?
I haven't thought about this for 15 years, so I don't, but I know I don't know.
I mean, one could define some kind of Q analog of tensor product multiplicities which would arise from this, and maybe compare it to known ones and so on.
I don't know. I haven't thought about it.
Oh, let's thank the speaker again.